Alright guys, this is our last video for real zeros of polynomial functions. In this video we're going to talk about the rational root theorem. And the rational root theorem says that the factors of a polynomial's constant term divided by the factors of its lead coefficient make a list of all possible rational roots for the function. So right here, when we're talking about roots, we could also say zeros. Right? If those roots or zeros are real numbers, then they would represent x-intercepts. And when we're saying rational numbers, we're talking about roots or zeros that we can represent as fractions or whole numbers. Looking at this, if we've got our f of x right here, we have a lead coefficient of 2, so the factors of that lead coefficient would be 2 and 1. And we've got a constant of 10, and the factors here would be 10 and 1, 5 and 2. We can get a list of possible rational roots here by taking the factors of our constant and dividing them by the factors of our lead coefficient. So we're going to go through with one of the factors of lead coefficient at a time, and we want to take into account the positive or negative values that we will get. So right here, 10 divided by 2 is going to give us plus or minus 5. 1 divided by 2 is plus or minus 1/2. 5 divided by 2 will be plus or minus 5/2. And right here, 2 divided by 2 will give us plus or minus 1. Now I'm going to go through and divide everything, divide all the factors of the constant by 1, but I'm not going to take any repeats. So right here, 10 divided by 1 is plus or minus 10. I don't have that as a possible root yet. 1 divided by 1 is plus or minus 1. We already have that, so we won't write it down. 5 divided by 1 gives us plus or minus 5. We actually already have that one. We don't need it. And 2 divided by 1 gives us plus or minus 2. So right here, this is the list of possible rational roots or zeros for our polynomial. Now, it may be that all 4 of the zeros for our 4th degree polynomial are in this list. It may be that some of the zeros, but not all of them, are in this list, or maybe that none of the zeros are in this list if we don't have any rational roots to this polynomial. What we're going to do when we use the rational root theorem to find all the roots, though, is we're going to say we need enough roots to divide out with synthetic division to get our polynomial down to a quadratic. Once we're down to a quadratic, we can use the quadratic formula to solve for those last 2 roots. So we need, in this case, at least 2 of these roots to be actual roots of our polynomial. So what we're going to do here is we're going to take a look at the graph of our function, because if any of these possible roots are actual roots, then they're going to represent x-intercepts. So we'll go ahead and type it into the calculator. So we've typed our polynomial into the calculator now, and we're going to take a look at the graph of this polynomial. Waiting for it to come up. There it is. So right here we're seeing what looks to be 4 places where we're crossing the xy axis, and now what we want, or crossing the x-axis rather. So now what we want to do is to take this graph and compare it to the rational roots that we're seeing here, to see which of these rational roots look like they could be probable roots, right? So we're going from possible roots to probable roots. And we're going to say we're a probable root if we're in this list and it looks like we might be an x-intercept. So right here, looks like -2 might be one. So right here we can say x equals -2. Looks like we might have 1 at 1/2. That could be a possible x-intercept there. And then maybe over here at 5/2. So x equals 5/2. Now what we're going to do is we're going to use synthetic division to determine which of these probable roots are actual roots. If any one of these probable roots or actual roots, when we use synthetic division, we're going to get a remainder of 0, and then we will have effectively divided out the linear factor that the root represents. So right here, we will start with -2, and we're going to take the coefficients of our polynomial, which are 2, 3, -12, -15, and 10. I'm not missing any terms, so I don't have to put in any zeros for placeholders there. And right here, our first step is going to be to drop that first coefficient. So we drop that 2. We multiply diagonally and then add vertically. So this is going to be a -4, and that's going to be a -1. This is going to be a +2. It's going to be a -10. Then right here we get -2 times a -10 gives us 20. And we add and we get 5. And now we've got a -2 times a +5. Looks like a 5. Is going to be a -10, and when we add these two guys, we get a remainder of 0. So right here, this -2 has turned out to be an actual root. And what we've done here is we have divided out the linear factor that root represents with synthetic division. Now we don't want to go back to our original polynomial. We want to take the coefficients and write the cubic that we've got as the quotient here. So we've got 2x cubed minus x squared minus 10x plus 5. And this is the cubic that we get after dividing out the linear factor x plus 2 from our polynomial up top. Now what we're going to do is see which of these next two guys looks like they might be an actual root. So right here, give our next one maybe 1/2 a shot. And right here, when we do synthetic division with 1/2, we're going to take the coefficients now of our cubic. Remember, we want to get down to a quadratic so that we can use the quadratic formula to find those last two zeros, right? So right here, we take the coefficients of our cubic, 2, -1, -10, and 5. I'm going to drop that first coefficient of 2, multiply, I get 1, add, I get 0, multiply again, I get 0, and then add, I get -10, multiply again, I get -5, and add, I get 0. So right here, it turns out that 1/2 is also a root of the polynomial, and the linear factor it represents is one of the linear factors we need to multiply to get that original polynomial f of x. Now what we've done right here is divide out the linear factor that the 1/2 root coincides with, and we're left with the quadratic. So we've effectively factored out two linear factors and got down to a quadratic. When we write our quadratic here, we're going to have 2x squared, and then right here we've got a 0 for our linear term, so that's really just -10. Now at this point, if we're solving for our zeros, we can set this guy equal to 0, and we don't even need to use the quadratic formula because we can just solve for x directly here. So we'd say +10 and +10. Now we've got 2x squared equals 10. We divide by 2, and right here we've got x squared equals 5. When I take the square root, I get plus or minus the square root of 5. Now, the square root of 5 is an irrational number. So right here, we've got x equals the positive square root of 5 and x equals the negative square root of 5 as two irrational roots. Right? And these are two roots that were not in our list, right? So basically, with our two rational roots, x equals -2 and x equals 1/2, we've got all four roots of our quartic polynomial up here. We can say, because we've already found all four of our roots, that x equals 5/2 would not have worked out for us with synthetic division, and neither would any of our other possible roots. All right, so right here, what I want you guys to do is to give one a shot. We're going to go ahead and try this one right here. I want you guys to go through and see if you can factor out enough of the possible roots to get down to a quadratic, and then from there we're going to use the quadratic formula to solve for those last two roots are zeros. Okay, so right here, the factors of the lead coefficient are the factors of 1, so that's 1 and 1. And right here, the factors of 10 are going to be 10 and 1 and 5 and 2 again. And right here, because the factors of our lead coefficient are 1, we can just take the factors of our constant and list those plus or minus as our possible roots, right? Since when we divide each of these guys by 1, we're really just going to get that number. So right here we've got plus or minus 10, plus or minus 1, plus or minus 5, and plus or minus 2 as possible roots for our f of x right here. Now again, we're going to use the calculator to narrow down our search. All right, so typing into the calculator and graphing it, we see this picture right here, and we've got two x-intercepts, which is promising. So we'll take this guy over to our notes, and right here we can say that from our list of possible roots, it looks like x equals -1 and x equals positive 2 look like probable roots. So these two guys might be actual roots. Probable actual roots or x-intercepts for our function. So right here we're going to use synthetic division. We'll take -1 first, and right here we'll take the coefficients 1, -5, 7, 3, and -10. Drop our 1. Right here we've got -1 times 1 is -5. That's -6. That's going to be 6, and that's going to be 13. Now right here we've got a -13 and a -10, and right here we're going to get a positive 10 that combines with our 10 and gives us 0. So right here it turns out that -1 is one of our actual roots. And right here we've divided out the linear factor that coincides with that root, and we are down to the cubic, that is x cubed minus 6x squared plus 13x minus 10. Now right here we're going to continue this process and try out 2. So right here we're going to say synthetic division with 2. We'll take the coefficients of our cubic now to get us down to a quadratic. So we've got 1, -6, 13, -10. Drop our first term. We've got 1. Multiply, we get 2. This is -4. Right here, -4 times 2 is -8. This is going to give us 5. 5 times 2 gives us 10. And right here, when we add, we get 0 as a remainder. So right here, these turn out to be the coefficients of the quadratic that we're going to get when we divide out the two linear factors that coincide with our roots. And that is going to be x squared plus, or minus 4x rather, and plus 5. Now we set this equal to 0 to find our last two roots, and here we can use the quadratic formula. So right here we've got an a value of 1, a b value of -4, and a c value of 5. And using the quadratic formula, we get x equals -4 plus or minus the square root of that -4 squared minus 4 times our a term of 1 times our c term of 5 divided by 2 times 1, and x equals 4 plus or minus, and then right here this is going to be 16, and that's going to be minus 20, so that's going to be a -4. So square root of -4 over 2. What are we seeing here? Turns out we've got an imaginary 0. In fact, two imaginary roots are zeros. We've got 4 plus or minus, and then 2i over 2. So our last two roots are going to be x equals 2 plus I and x equals 2 minus I. And that explains why we're only seeing two x-intercepts here from our coordinate, right? So we wouldn't have been able to find these in our list of rational roots, obviously. They're imaginary, and they're not going to represent x-intercepts either. So we've got our two rational roots of -1 and right here 2. and we've got two imaginary roots of 2 plus I and 2 minus I, we can in fact see how it might be that this function actually has no real roots. If we were to add, let's say, something like 15 to this function, that would move it up 15, and we wouldn't be crossing the x-axis at all. And in that case, all of our roots or zeros would be imaginary. If we want to write f of x in its linear factorization, basically what this is going to mean is writing it as a multiplication of its real number linear factors. So right here, these two imaginary roots, I would want to represent them as the quadratic x squared minus 4x plus 5. So right here, a linear factorization is going to look like this. F of x equals, and then I've got the linear factor that goes with negative 1 as the root, so that's x plus 1. And then right here, x minus 2 for the root of 2. And then right here, I've got x squared, and then this is going to be minus 4x plus 5. So in general, when we're writing out linear factorization of our polynomial, it's not quite good form to incorporate imaginary numbers into that expression. So we would say that we would write the multiplication of the two roots that give us our imaginary, or the multiplication of the two linear factors that give us our imaginary roots as this quadratic right here. We say that this quadratic is irreducible over the reals because it has imaginary zeros. So that's a little bit of vocabulary for you at the end. This is our last video. Only 16 minutes, not bad, guys. We're cutting down the time, and I'll cut off some questions from the homework too. All right, so by study hall, I'll already have done that. So we'll work on a worksheet tomorrow in class, and happy studying, guys.